Section 7.2, Estimating a Population Proportion. We saw with previous distributions like the binomial distribution or even the normal distribution that the proportion of a sample or proportion of the number of successful trials in the sample was represented with P. So whether it was given as a percentage, so 60% of voters or 25% of the men in a weight loss study, anything like that, we've seen that letter before that P. And we often use it as a probability. But probability, proportion, percentage, they're all kind of used interchangeably. Now we're interested in estimating the proportion of the population. Oftentimes we don't know information about the population, but we can use a statistic from the sample to estimate a parameter from the population. When we use the sample proportion as an estimate, we call it p hat. The sample proportion p hat is the best point estimate of the true population proportion p. So we don't really know the population proportion. Anytime we're given a statistic about, or a parameter rather, that 75% of men enjoy watching football. Well, we don't really know that all men, the percentage of all men that enjoy watching football. We can only estimate it. So we take an estimate from the sample, but it's giving us the best estimate of what's really going on with the population. Because p hat is only an estimate, of course, there's the possibility of error. When stating our estimate of the true population proportion, we also want to state any error that is possible. A confidence interval is a range of values that contains the true population proportion at a certain level alpha, called a confidence level. So confidence interval is between this number and this number, and we're saying that that interval contains the true population proportion, which we don't know, but we're pretty confident that it's within this certain range. Alpha is the level of confidence. So either we are 90% confidence, or 95% confidence, or 99% confidence, or maybe only 80% confident. So that's what we'll be looking at in this section. Now the confidence level is the total area in the middle of a normal curve. So if you remember what your normal curve looks like, what we're saying is the confidence level is here in the middle, which is considered 1 minus alpha percent. So the tails contain the leftover, and that's where alpha comes from. So for instance, excuse me, so the Greek letter alpha represents the total area in both tails. Since it's symmetric, we can split it right down the middle, and 1/2 is on the right tail and 1/2 is on the left tail. So let's say we're interested in 95% confidence level. That means 95% is right here in the middle, for example. So 95% is in the middle. Well, that leaves 5% left over, because remember, our total area under a standard normal curve is 1. Well, it's not 5% on each end, it's 5% total. So that means this end would be 2.5%, and this end would be 2.5%. So that's where we're dividing that alpha by 2. So 1 minus 0.95, that's an extra 0 there, that should be 0.95 like that, or 0.05. Then we take that divided by 2 and we get 0.025. So then z sub 0.025, remember we looked at that back when we learned about looking up normal table values. That's the z value that will give an area of 0.025 in the left tail. So this, we're looking for a z value right here, and that's ultimately what we'll use to calculate our confidence interval. So more formally, here's our formula for the confidence interval and the margin of error for population proportion. So remember, P without the hat is the true population proportion. We don't know it unless we're able to take a census. Remember, a census is when we do have access to every member of a population. Usually we don't, but so when we don't, P is the true population proportion that we probably don't know. But to estimate it, I'm going to take my P hat, which is the estimate, probably from the sample, subtract off the error, so that's a little bit less than what the true population proportion is, take P hat and add on the error, so it's a little bit more than what the true population proportion is, and that's what gives me my interval. Well, what's E? E is calculated by taking Z alpha over 2, which we just talked about above, and multiplying that by the square root of P hat Q hat over N. And just like before, Q hat is equal to 1 minus P hat. And that's called the margin of error. Now, before we can find a confidence interval for a population, we need to check that 2 requirements are met. Or not 2, but quite a few actually. That a few requirements are met. One of the requirements, the sample must be a simple random sample. So although we've learned a lot of different sampling techniques such as stratified and cluster, we don't want anything like that. We want something just simple random sample where you randomly select members to be a part of the sample. Another condition that must be met, the 4 conditions for the binomial distribution must be satisfied. Remember, those are that the trials have to be independent, there must be a finite number of trials, there can only be 2 possible outcomes, a success or a failure. Probability of success must remain the same from trial to trial. So if you need to review those, go back and look at your notes on the binomial distribution, but those 4 conditions must be met. And then finally, there are at least 5 successes and 5 failures. Another way to test that is if n times p is greater than or equal to 5, but also that n times q is greater than or equal to 5. Both of those have to be met. So all 3 of these conditions should be met, and then we're ready to construct a confidence interval. Once we do that, this is how we find the confidence interval. First thing you want to do is find the critical value, z sub alpha over 2. And we'll practice that here in a moment, but remember, when you're finding the z value, you don't look on the sides, you're kind of searching in the middle for a value that comes as close to what you're trying to find, and then you look on the side to see what z value that is. You can either use your standard normal table, or you can use your inverse normal function on your calculator. The second step, calculate E, the margin of error. So once you have that z value, you're going to multiply by the square root of P hat Q hat over N. And third, use that value and the sample proportion P hat to find the confidence interval lower and upper limit, so what that range is. So let's try this out with an example. Example 1. A random sample of 5,792 physicians in Colorado showed that 3,139 provided at least some charity care, i.e. treated low-income people at no cost. These data are based on information from state healthcare data, utilization, spending, and characteristics from the American Medical Association. Part A. Check that the requirements are met for this scenario. So before we get to calculations, we want to check the requirements that we look at above. So first, the sample must be a simple random sample. Sounds like it to me. We have these 5,000 plus physicians, and randomly 3,000 or so, 3,000 or more were selected, and it told us that right here in the beginning, a random sample, so I think that's okay. Then we want to check that the conditions for the binomial distribution are met. I tend to check the conditions for a binomial rather randomly. I don't necessarily always go in the same order, but independence, I'll check that one first. We can pretty much assume that what one physician chooses to do is independent of another, so we'll say that that's met. Only 2 possible outcomes are possible. Well, yeah, either the physician chooses to do some charity care or they don't, so that's met. The probability of success, meaning that the physician does some charity care, is consistent from, or is the same from trial to trial. In this case, if we were to use a proportion to state and use that as the probability that a physician would do some charity care or not, then we can say that that's true. And then finally, are there a finite number of trials? Yes, because there's only so many physicians in Colorado. So I think that all of those are met. Then we had that there are at least 5 successes and 5 failures. We more than qualify for that. We're ready to move on. Okay, part B, where the calculations come in. Let P represent the proportion of all Colorado physicians who provide some charity care. Find a point estimate for P. So our point estimate is going to come from this sample. So P hat would be the proportion, the 3,139 who do provide some charity care out of 5,792 the physicians in Colorado, the sample of physicians in Colorado. And that gives us 0.54195 if you go out a few decimal places. Okay, so P hat, remember, is the point estimate for P, which we probably don't know. Part C, find a 99% confidence interval. Well, remember back with our steps here, the first thing we want to do is find that critical value Z alpha sub 2. Well, first we need to find alpha. Well, alpha is 1 minus our confidence level. And our confidence level is 0.99, so that means we have 0.01. But remember, that's the total area in the 2 tails combined. So to get just a single tail, I'm going to find alpha over 2, take my 0.01 and divide by 2, and that gives me 0.005. Now I'm ready to find that table, find that value Z sub 0.005 on the table. Okay, so I want to be in the tail, so I'm going to use my negative table, and I'm looking for something that is as close to 0.005 as possible. And it looks like right in here we have 0.0051. We have 0.0051 and 0.0049. You could either choose one of them, or sometimes you can split the difference. So sometimes I leave the decision up to the students because either answer is going to be so close it shouldn't matter. But if we look back over to the side, we'll see that we're at negative 2.5, either 2.57 or 2.58, and some people would even go in the middle here and say 2.575. So I'll let you make that decision. I think I'll go with that middle value. So our Z score, 0.005, is negative 2.575, and we also have it on the other side, so positive 2.575, but we'll use the positive value. Now we're ready to calculate E. Remember, E was our Z sub alpha over 2, which we just found, times the square root of P hat Q hat divided by N. Double check that formula. Okay, so we already have the Z sub alpha over 2. That's 2.575. P we found to be 0.54195, P hat rather. Q hat, I'm just going to subtract that from 1, so I get 0.45805 divided by N, and our sample size was 5,792. And this comes out to 0.01685774142. Let me encourage you when you're doing these intermediate steps to carry as many decimal places as possible. Let your calculator do that for you. Even though when I'm writing things down I might only write 4 or 5 decimal places, let your calculator carry as many places as possible, and that will increase your accuracy. So here we have the 0.016 or so for E. Now to find the interval, I'm going to take that number and add it to P hat. So for the lower bound, I would say 0.54195 plus 0.0168, and so on and so forth. And for the upper bound, it would be 0.54195 plus 0.0168. I know I'm squeezing this in down here. So the confidence interval, if we wrote it this way, would be from would be from 0.53 to 0.56 after rounding. So just as you notice when you do your homework, do not round to the very, very end. It can really throw off your accuracy, even if it's into the third decimal place. So try to let your calculator handle those really large numbers, large in the sense that they have a lot of decimal places. Don't truncate them too much. And you should get, your answer should agree with your homework. Okay, so we found this confidence interval from 0.53 to 0.56. Well, what does that mean? It's really important that the confidence interval be interpreted correctly. In our above example, we can interpret our interval this way. We are 99% confident that the interval 0.53 to 0.56, which is another way to write it, contains the true value P, the proportion of all Colorado physicians who provide some charity care. Be really careful how you state this, because it's not correct to say there's a 99% chance that the true value of P will fall in between 0.53 and 0.56. Although those seem similar, they're not really similar. So the correct way, we are 99% confident that the interval contains the true value, as opposed to saying the value falls in there. And the difference there is because this 99% that we're getting is saying we could come up with various different intervals, and 99% of the time it's going to contain the true proportion, and maybe that one time it's not. So it's not about the value falling inside of it, it's that the interval contains it. So be very careful when you go to interpret these results. Let's take a look at example 2. In a survey of a random sample of 35 households in the Cherry Creek neighborhood of a quiet suburb, it was found that 11 households turned out the lights and pretend not to be home on Halloween. Compute a 90% confidence interval for P, the proportion of all households in Cherry Creek that pretend not to be home on Halloween. Interpret your results. Well, this time, compared to the previous example about physicians doing charity care, we're given the proportion up front that, oh no, we're not. I was looking at a different number. Okay, so 35 households and 11 of those households turned out the lights. So first we need an estimate for P. So P hat will be 11 over 35, which is 0.3143 if I round to 4 places. But when I go to do my other calculations, I'm going to let my calculator handle all the other digits that come behind that. So first I have P. The next thing I need to do is find the z-value. So first I know that alpha is equal to 1 minus 0.9, which is my confidence level, the 90%, which is 0.1. But to get alpha over 2, I'm going to take that 0.1, divide by 2, and get 0.05. So I want to look up z sub 0.05 on my table. So remember, that's the area in the tail. So 0.05, not 0.005, that's what we looked at last time. Okay, looks like we're somewhere down here to find that value. Right here, 0.05 and 0.495. And those seem like they're on either side of the value we're looking for. So 0.05 and 0.045. We have 1.6. The z-score that goes with that is 1.64 or 1.65. Again, you could choose either one, or you could split the difference and say 1.645. So let's see, I think I'll do 1.645. So we go back here, and Z, I don't need to write that again, Z 0.05 is 1.645. And don't forget, you could also do this on your calculator with the inverse normal function. If you were to type in 0.05, you get negative 1.6448 back, and you could round that to 1.645. Okay, now I need to find my margin of error E, which is Z sub alpha over 2, square root of P hat, Q hat over N. We found Z sub alpha over 2 to be 1.645. And we're going to multiply that by 0.3143 for P hat. 1 minus 0.3143 if you want to think of it that way for Q hat. All over N, well, the sample was 35 households. So again, I'm going to let my calculator handle this number here, this 0.3143, because it really was 0.3142857. It goes on for a while. But I'm going to type this all in. Okay, and I get that E is equal to 0.12908, and there's certainly a few more places after that. So now for the confidence interval, I'll take P hat plus, or let's do the lower one. P hat minus E is one side, and P hat plus E is the other side. So this would be 0.3143 minus 0.12908, whereas this would be 0.3143 plus 0.12908. Again, letting my calculator handle the long decimals. And I get 0.1852 here and 0.4434 here. So the confidence interval, or I should say specifically, a 90% confidence interval is 0.19 if we round to 2 decimal places, and 0.44. So my interpretation, we are 90% confident that the interval 0.19 to 0.44 contains the true proportion of households who pretend not to be home on Halloween. And remember, it's not okay to say we're 90% confident that that the true proportion falls in this interval. We want to say that this interval contains the proportion. Okay. Next, moving on to determining the sample size. Well, what if we want to produce a certain confidence interval at a certain level, alpha, but we don't know how large of a sample to collect to make it happen? Well, if we take the margin of error formula and solve for n, we get the following. So this is a formula to determine the sample size for estimating a proportion p. So n, remember, is our sample, and what happens is we take our z sub alpha over 2, square that, multiply it by p hat and q hat, and divide by e squared. That's if we do have an estimate for p hat. If we don't, then we use 0.25 as an estimate for p hat times q hat, and everything else stays the same. Okay, now let's take a look at example 3. What percentage of your campus student body is female? Let P be the proportion of women students on your campus. A. If no preliminary study is made to estimate P, how large a sample is needed to be 99% sure that a point estimate P will be within a distance of 0.05 from P? Okay, for part A, let's first identify what we do know so far. So we know that our confidence level is 99%. So that means alpha is 1 minus 0.99 or 0.01. But if I want those tails, alpha divided by 2, that means 0.01 divided by 2 or 0.005. The other information that we're given is the error. So this time we know the error is the sample we're trying to find. Well, if p hat is going to be within a distance of 0.05 from p, that means either above or below. So that's our error. So E is equal to 0.05. Now in our formula for finding the sample size, we know we don't know P this time, so we're going to have to use the second formula. We know E, and we have to look up Z alpha over 2, so let's do that. So I need to find Z sub alpha over 2, which in this case is Z sub 0.005, and we found this value before, but it doesn't hurt to practice looking it up. So we go to our table, and I'm looking for 0.005 or something very, very close to it. And we found it right here, but I think we went ahead and said 2.575 to split the difference. So our z-score is 2.575. So since we don't know, we don't have an estimate for p hat, we're going to use that second formula, which says z sub alpha over 2 squared. So we take our 2.575, square that, multiply by 0.25, and divide by E squared. So 0.05 squared, and that gives us, and I get 663.06. So if we were round to the nearest whole number, that'd be 663. So what that number means is in order to produce a confidence interval where we are 99% sure that that interval contains the true proportion of female students on campus, we would need a sample at least as large as 663. Let's take a look at Part B. A small survey was conducted, and it indicates that approximately 54% of college students on campus are female. Answer Part A this time. Answer Part A using this estimate for P. So this time we do have some estimate of what the proportion could be. So now we know that P hat is equal to 0.54. Then we can go ahead and say that Q hat is equal to 0.46. So this time to find N, I would still use my same z-score, 2.575. That gets squared, times 0.2, well, not times 0.25 this time. This time we'll use P hat and Q hat. So this will be 0.54 times 0.46 all over 0.05 squared. So the only two things that changed were these numbers here. And multiplying that out, I get 658.8189. So if we were to round that up to the nearest whole number, we'd say 659. So when we do know a little bit more information about the proportion, even if we just have an estimate, you'll notice that our sample size could be a little bit smaller. So make sure you notice the difference between these two, whether you are told a point estimate for the true proportion or if you're not. Depending on what information you have, you'll have to choose which formula to use.